welcome back. So, last video on relativistic Bennett vorticity, we dove into that side of the theory, right? Into the fact that, well, the axial velocity in the Shumlak-Hartman Criterion is the MHD velocity, which is different from the drift velocity that is the basis for this integrable current density that comes from this axial flow, okay? And by the way, just real quick, this is also a solution to Navier-Stokes. It is a one-dimensional solution to Navier-Stokes. It does not solve the full 3D system. So it's a simple flow, category 1 solution. We've got a number of them. And it solves it only on the z equals 0 plane and the r equals 3 CBT ring. Okay, which is another video entirely. I'm just saying that. Could have came to my head by the hiccups. All right, so we did that, and then we said, okay, how can we link the drift velocity with the MHD flow in a way that's physical? And there's a couple ways to do this. One way is to say the electrons are stationary. That doesn't make any sense to me. That's the non-relativistic way. Because in the non-relativistic case, the ion mass dominates the electron mass. So the ions end up carrying the current. But in the relativistic case, when the electrons are relativistic and the ions are non-relativistic, which I argue is more physical than definitely the converse, although I wouldn't necessarily rule anything out, right? But when that is the case of relativistic electrons and non-relativistic ions, then, well, it's the electron flow that dominates the MHD flow. And also, this case allows us to say, oh, cool, well, since the electrons are dominating the MHD flow, let's just go ahead and take the ion velocity, we'll just say they're stationary, just take it to be 0. Of course, that necessitates us to do a relativistic analysis. Now, again, I'm going to say this again. What we did last time was not a full covariant derivation. We did not start from a 4-vector for flow velocity and study the equations of mass, momentum, and energy in the context of a relativistic magneto-hydrodynamic fluid, okay? So we didn't do that. Instead, what we did is an ad hoc derivation. We simply said, okay, we're traveling close to the speed of light. That is going to cause space to contract. So that means that in the lab frame of reference, the density is going to relativistically contract. Also, because relativistic energy increases as you get closer to the speed of light, we incorporate that, treat that as our mass increasing. All right? So we made those modifications, and we found that the structure of the momentum balance remains the same. And it's because of the Z-pinch ansatz. All the inertial force and the steady density. Sorry, not just the steady density. The fact that our density is uniform. The uniform density. Right? And because of those facts, the inertial terms, the inertial forces all went away. And we got these gamma squareds we didn't want to really deal with. And they disappeared. And then it doesn't matter that there's a gamma that shows up in the current density. That doesn't matter. All right? The structure still remains the same. So we can exploit that. We can exploit that by saying, okay, we have an integrable current density here. And if you treat the flow as the MHD flow, we have a shear flow stabilized Z-pinch. So what do we need in the relativistic case? And it's written right here. What do we need in the relativistic case to get the same current density as in the non-relativistic case, that integrable current density? And you might say, Matt, where did this negative sign go here? It doesn't matter. It doesn't matter. It's just a direction. Right? It's just a direction. And we carried the math through, and we found, here's a value for the electron velocity. That relativistic electron current. Here it is, based on the axial flow. And then the next question is, great, okay, cool. This is the real important question. Cool, you've derived this. That's not so hard. but is it still shear flow stabilized? And that is a question we're going to answer in this video, all right? So I'm going to erase all this, and we're going to get to it. Probably shouldn't erase all of this. I'll rewrite the things that I erased that I shouldn't have. And this is something that physicists do a lot of. Like if you ever talk to a physicist, they might say something basic, right? And you might feel that it was condescending. But the thing about physicists is what I've noticed, and I noticed this a lot in graduate school, is that they're not really saying basic things to be condescending. They're saying basic things for two reasons. The first reason is that it's just repetition. Repetition is what builds that understanding. All right? So before I go any further erasing the board, let me just put down what's important here. This is the cubic pure flow Bennett Shumlak-Hartman vortex. And I like that name actually, because Hartman deserves to have recognition here too. Okay? And then we'll get off to the races here with the relativistic Shumlak-Hartman Criterion. I won't go through the whole, I won't relitigate the argument of how we connect the MHD flow. I think at this point we're pretty clear on how we've connected the MHD flow to the electron flow that's presented here. Yeah, let me rewrite this. And the other part about this that I won't relitigate is I won't relitigate why this goes to zero. It is simply because L is going to infinity in the ideal magnetohydrodynamic case. That is totally valid. The one thing that can blow it up is if your magnetic field goes to infinity. And I haven't derived the magnetic field in a video yet, but it's in the supplement. I'm not saying everything in there is, well, I don't want to say that it's wrong, right? That mathematics is, there's a lot of mathematics in there, okay? And you can find the magnetic field derivation. That's one solid piece of mathematics. It is amenable to U substitution or a computer algebra system. And I'll have a video going through the magnetic field, but we got to go through this one point at a time. We've gotten stuck in the momentum equation because of this relativistic repair that we're doing, right? And so we can see that we have the Shumlak-Hartman Criterion. And the Shumlak-Hartman Criterion, it'll have UZ, but remember that this UZ really is, at best, it's the drift velocity. It's the Z component of the drift velocity. And it's only because we have stationary ions that we can link it to the electron flow, and that requires relativistic electrons, and we found that this is what it looks like, okay? When we apply self-similarity. And then again, down here, so we have DUE, just going to put that there, right? We went over that last time. C over C squared minus UE squared, and that is greater than zero. That is the Shumlak-Hartman, relativistic Shumlak-Hartman Criterion in the context of ideal MHD, without a running magnetic field, which it doesn't. And I'll show that in a future video. Okay. What's important in this video is to determine whether or not this is satisfied. Because if it's not satisfied, hey, blew it out of the water. I guess I'll go back to trying to program GPUs and grinding leak code. But fortunately, it is satisfied, and we're going to show it. Okay, so the first thing we got to do is we just simply got to plug and chug. All right? And now what we're not going to do, though, is we are not going to throw away C squared minus UE squared. We are not going to do that, because that would lose information. This is relativistic. We need to carry this through. It looks ugly, but it will work out. So let's start off by me looking at my notes. Okay. So the first order of business is, what is due dr? Okay, well, what is it? All right, well, due dr is going to be, and the great thing here is that we have the square root of c squared plus uz squared on the bottom, but other than that, we don't really have that ugly of an expression here. Now, if you're out there watching and you're a student, okay, don't ever do the quotient rule. Just don't do it. You don't need it. All you have to know is the product rule and the power law. All right, so here we go. This equals C times the shear of this guy and then minus 1/2 uz all right, and then remember the chain rule as well. What's the derivative of uz squared? It's 2uz times the shear of uz. Okay? Well, that's nice. And this is really nice because we have a factor of uz prime in both. The shear shows up in both. That means that we can pull it out. And now what we want to do is we want to multiply this guy top and bottom to get a common factor with this fellow. Okay? So we're going to multiply it by c squared plus uz squared over c squared plus uz squared. These twos cancel. uz squared. Now, this is something in physics that you'll notice happens in a lot of successful derivations. Things start to cancel. The things that you want to cancel, they do. All right? Trying to lunge down again. I just don't have enough room, really. Okay. So that we have C, uz prime, just going to try and save some space here. And then the amazing thing is these ugly uz squareds go away. We are left with c squared over c squared plus uz squared to the 3/2. Okay? That is, and then we have this factor of c as well out front, right here. So that goes in, and so I'm just going to erase this and just add this cube here, okay? So that is our relativistic electron flow, and that's the shear of it. We have the shear of our original flow, okay? Our cubic pure flow, Bennett Shumlak-Hartman vortex. And then we have this relativistic correction. So, where do we go from here? Where do we go from here? Where we go from here is we plug in uz squared and we plug in uz prime. There's no two ways about it, y'all. That's what we got to do. You just got to plug and chug. Okay? So what I'm going to do, because I'm running out of room on the board, is I am going to go up here and I'm going to write that down. I'll write down here's the shear. Excellent. Now let's erase this and let's work out what the shear of the axial flow is. The basic, again, the cubic pure flow Bennett Shumlak-Hartman vortex. And we'll also determine what that is. The denominator, that's the other ugly part of this. But here's the cool thing, is that we have these squares. So when you square squares, they become quartics. And maybe what will happen is we will find a way to get things to cancel. I don't know. Let's see. Let's see if we can do that. Where are my notes on this? Here we are. Sorry, thank you for your patience. There we go. There's the page I wanted. Don't forget, we also have this term. So let's actually, before we do that, let's deal with this term. What's the square root of c squared minus ue squared? All right? Well, we know what ue squared is. It's just this guy. So this is c squared minus c squared. Hey, looks like there's going to be a factor of c that gets pulled out. That's also something you want to see. You want to see factors getting pulled out and simplified. The more complicated some math is, the more you're screwed. The more chance there is, I should say. All right? So what is this? This is just c. Pull that out. Now we have a 1. I'm going a little fast here because, well, speed is of the essence. And that is squared. Yep. So again, use these squares cancel. We love to see that. That is exactly what we want. Yep. And what we get is we get c squared and this is another really good thing. This actually, in my opinion, is probably what saves the whole derivation here, because notice this 3/2, that's ugly. That is ugly. We don't want to deal with 3/2. We do not want to deal with 3/2. But guess what's less ugly than 3/2? When you have a square root over 3/2 of the exact same argument, then you have a loss of the radical. All right, well, nothing to do but to just plug this in to here, okay? So what's this? Well, it's UZ prime c cubed and then we've got another c here, a c squared on the bottom, and this comes to the top. I hope y'all can see that. Sorry, my handwriting's a little cramped. I also got to keep, I'll erase this and write it better. All right? what does that equal? That equals UZ prime that equals UZ prime, okay, C squared over C squared plus UZ squared. Now this is nice. This is really nice. Look how ugly this was. Look how nice this is. Okay? Now this is when we can plug in UZ squared and UZ prime, all right? So let me just go ahead and let me box this. Let me just go ahead and we'll just do that. But first we got to figure out what UZ prime is, okay? So I'll do that over here. And you know, I know that I'm erasing things, but hey, you can always pause the video. Speaking of which, let me check and make sure it's not paused. Okay, good, we're still rolling. Very first video I shot, it died in the middle. I ran out of space on my phone, so I'm leery of that. All right, well, what's UZ prime? We have not showed it yet, but we're going to show it now. UZ prime, very simple. Product rule plus the power law. All right, that's easy. And again, nice things are going to happen. Nice things are going to happen because to get a common denominator, we've got to multiply by r plus CBT over r plus CBT. And most people use different things in this field. They use A for the pinch radius. When I talk to ChatGPT about this, it tells me to use A for CBT. It is what it is, people. So we have 2r, r plus CBT, and we'll get some nice cancellation. We'll get some nice cancellation, and what we'll do we'll find that this is what UZ prime is, right here. All right, excellent. What's UZ squared? Well, that's honestly way easier. Turn this into a 4. Add a 2 there. Turn that into a 4. Okay. I am running out of room, though. But we can finish this. We'll finish this down here. And we have c squared over this quantity. All right? So here's where my eyes go when I see this. I go to the fact that there's an r plus CBT cubed, and there's an r plus CBT to the 4th. We're going to get some cancellation. All right? So we have 2 UZ naught CBT, okay, c squared, and then what happens? Well, we get a common denominator in the denominator, all right? And then that ends up getting flipped on top. And that leaves us with, then over here, we have 1 over c squared just like that. That and that cancels. All right, and what are we left with? Well, remember, this is the left-hand side of the relativistic Shumlak-Hartman Criterion. So we've got a 0 that we can just throw things into. And again, we can throw things into that 0 because, well, L went to infinity. So if something on the other side doesn't blow that up, we're all good. And nothing is. The magnetic field is self-similar to the case in the non-relativistic plasma current density. When you insert this for the drift velocity, all right? The drift velocity that supports the plasma current density. Okay? So let's just go back up here. And there should be an R as well. Don't forget that R. And then on the bottom, we're going to have a c squared okay? That is the left-hand side, and this has to be greater than 0. Let's remember that. Now, when we take the limit as r goes to 0, what we get is 0 greater than 0. But here's the thing. Even though it was originally investigated, and the original paper, the 1995 Shumlak-Hartman paper, says greater than, in the decades since that result, this is going to be better for my knees and they won't get rug burn. In the decades since that result, the community has actually found that you can add an equals to. That if the left-hand side, if we are at the threshold shear, because that's what this really represents. It represents the threshold shear. Now you might say, Matt, what sense does it make for this thing to be shear flow stabilized if you're investigating a threshold shear that's 0? But that's because of the limit that we're studying. That's because of the, not the limit, the regime. Ideal magnetohydrodynamics. And also, again, because of the exact current that we're looking at. The magnetic field has a structure where it goes to 0 as the plasma radius does, where it doesn't run to infinity. For example, if it started at infinity, what sense would that make? Probably, it would definitely violate Ampere's law unless there was a singularity at 0 in the current density. So we plug in R equals 0 for this, and we get 0 over, not 0. It's not 0 over 0. It's 0 over 0 plus c squared cdt to the 4th. That's 0. So it satisfies it weakly. All right? It satisfies it weakly in that sense, right? Marginally, I guess you could say. And if we don't plug in R equals 0, which is to sort of look at the limit of minute spaces. Well, what else could we do? Well, one thing we could do is we could say, hey, minute spaces, what about minute pinches? Okay, let's plug in RP equals 0. Well, this CBT scales as RP to the cubed. So that's going to outpace anything. That means CBT goes to 0. So we have 0 on top over, again, it's not 0 on the bottom. It's R to the 4th times c squared plus UZ naught squared. So in that sense, in an arbitrarily small pinch, it's also zero or satisfied. The only problem that this runs into is when both R and CBT are zero. And fortunately, that's a pathological problem. We can get away from the origin. We can get away with saying, okay, screw R equals zero, screw what's going on there, because we can specify the boundary conditions to specify the state of the plasma at that point. And then we'll be fine, right? As long as the shear doesn't have a problem, as long as the profile we're working with doesn't have a problem. And it doesn't. It doesn't have a problem unless both of those things are zero, which again is pathological. So the last thing we should do is let's consider not arbitrarily small spaces, but just general ones. Okay? Well, what happens generally speaking? What happens generally speaking is that we can throw away this denominator. Just throw it away into there. It's not zero. It's fine to do that. We're not suffering from a divide by zero error, which would be another killer. If you've ever seen those proofs where people start with some algebraic expression and they arrive at something like 1 equals 2, it's because they divided by zero at some point. All right, that violates the field axioms. That violates the laws of real analysis, and you can't do it. So the shit breaks. All right, so when we throw away this denominator, what we find, and again, we can also throw away some parts in the numerator, all right? So we're throwing away the denominator, which implies that we have we can throw away a lot of things. We can throw away a c squared. We can throw away an r plus cdt. We can throw that away because it's not dividing by zero. Even if r is zero, cbt is non-zero, so it's not zero, right? And what we get, we can also throw this 2 away. What we get is uz naught cbt r is greater than 0. And guess what, y'all? That is always going to hold for a non-trivial problem. And even at the origin, it still is marginally satisfying the shear-flow stabilization criterion, the relativistic Shumlak-Hartman criterion. Therefore, this electron flow also describes a shear flow stabilized Z-pinch, right? Any solution that has a finite CBT, that gives a finite UZ naught, is going to satisfy this criterion. I rest my case. All right, thank you for watching. Thank you for following along. I really appreciate it. Please like and subscribe if you like the videos. And if you want to support me, then please consider donating to my coffee, my Ko-Fi. I'll write it up on the board. Coffee.com/Navier-Strokes. All right. I do need the support right now. Where my career has landed is it has landed in getting this work published. It has landed in exploring this problem that I came up with to stump ChatGPT, because it's the only thing I could think of. It was the only out that I had. If you ever played cards, if you ever played like Hearthstone, for example, the difference between like a good Hearthstone player or just a good card player, like a good poker player, it generalizes to any card game, really, any game of chance, is between that and a great player, is the great players, even when they're in a bad situation, even when things are like they're a turn or two from losing, they play to their outs. All right, So that's what I did. I just played my outs. The only out I had to stump ChatGPT with an hour left on the clock was, and nothing but Bennett pinch codes, was the only thing I could do is exchange the profile and get a number out of my Bennett pinch codes in that way. Now, it was a strange limit that I was studying, but that it is what it is. And so that's where my career has landed, right? I spent 4 months writing a pipeline, a GPU pipeline, a Vulkan pipeline for a startup to visualize user data and read it in a clean architecture framework. And I also wrote a research and development report that was close to 80 pages explaining, here's all the things you got to think about when you're coming up with a digital twin of a catwalk. And the answer is, you need motion capture. Just use motion capture. Don't try to simulate that. It's way too complicated. It will not work in an emotionally realistic manner. And then there's also people at the Max Planck Institute who have already come up with a body model, the simple body model, right? So go use that. But you need to pay for that. So that ended when it was clear that, they didn't want to pay for anything. All right, that's all I got. Thanks for watching, and I'll see you next time when what we're going to do is we're going to move beyond the momentum equation, and we're going to get into the energy equation. We're going to prove that this n equals 3 case is indeed the minimum energy state. All right, thank you for watching, and please tune in next time.